Algebra 2 Notes 7.2 Properties of Exponential Functions. So today we're going to look at the graph of an exponential and how we can move it left, right, up, down, stretch it, and reflect it. So let's take the original graph. This is the same one that we did yesterday. So choose some values for x, plug it in to 2 to the x. That will help us figure out what our y is. So you can just choose a couple of points there just to see what the original graph will look like. So 2 to the negative second. Remember, that's going to be 1 over 2 to the second, which is 1/4. So why don't you go ahead and fill out the chart and graph it. Go ahead and pause your video and then we'll jump down to the vertical stretch. All right, so your point should look something like that. Remember, there's an asymptote on the x-axis here. So when we connect our dots, we don't want to go below the x-axis. So it looks something like that. All right, so the first translation or transformation we're going to look at is the vertical stretch. So just as if we were doing a parabola, if you have a number out in front, 1/2 or a 3 in these two cases, what's going to happen is that 1/2 is going to take each y value and cut it in half. Okay, the 3 is going to take each y value and multiply it by 3. So we're going to take this original graph we graphed at the beginning and cut it in half for the first one. So if we look at this graph that's already done for us, we can see at 0, instead of going all the way up to 1, it only went up to 1/2. At 1, instead of going all the way up to 2, it only went up to 1. So it's just taking each of these original points up here and cutting them in half. Instead of going 4 to 4, it's only going to be 2, 2. Okay? So that's what that 1/2 does to it. What about a 3? What would that do to it? So what I like to do is graph the original and then graph the new one on the same graph. Okay, so here are the points from the original graph. Just jot down so that's y equals 2 to the x. But what happens if I take this times 3? So we're just stretching each y value by a factor of 3. So instead of this point being up 1, we're going to take that times 3. 1, 2. So now it's the point 0, 3. Instead of the point being up 2, we're going to take that times 3. So it's going to be up 6. Instead of up 4, times 3 would be up 12, which actually doesn't fit. Okay, instead of up 1/2, times 3 would be 1/2. 1/4 times 3 would be 3/4, and so on. And then we can just kind of sketch in that line. So the transformations are the same as they've been all year. Okay? All right, let's look at another one. Okay, if we look at that horizontal translation, again, it helps to have the points of the original graph in here. So I'll just put those in there real quick. 0, 1, 1, 2, 2, 4. We add negative 1/2, and then it's just going to go down. Okay, so there's my original. Now this one, if I'm looking at -2, which is inside the function, remember that's going to move it left and right. Okay, so if we are subtracting, that's actually going to move it to the right 2. So each point went 1, 2 to the right. 1, 2 to the right. 2 to the right. Okay, so it's just the same exact graph, but shifted 2 to the right. So go ahead and pause your video and see if you can do this next example. Again, I would start with those original points. So you had 0, 1, 1, 2, 2, 4. We could add 3, 8. Just to kind of help us have a starting point. So now move each of those points 3 units which way. Go ahead and pause your video. See if you can finish this graph. All right, so each point is just moving 3 units to the left. Okay, so if we connect the dots, we still have that asymptote at y equals 0. So this line can't go over the x-axis there. All right, let's go to the next one. Okay, the next one is the vertical translation. So this is in the function at the end, we're either adding or subtracting a number. So this one, since we're subtracting 3, that's going to tell me the whole graph will move 3 units down. So if I take my original points, I'm going to move them each 3 units down. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, and then it's going to be the graph that was 3 units down. All right, how about the next one? 2 to the x plus 3. So each point is moving 3 units plus 3. Which way would that go? So go ahead and pause your video, see if you can complete this second graph. Now something to notice on these graphs that move up and down is that asymptote moves also. So like on the first one, since you're moving that down 3 instead of the asymptote being at y equals 0, it now needs to be at y equals 3. Ours moved up 3 on this one, so instead of our asymptote being at y equals 0, it's now going to be at y equals 3. So if I connect those dots, I should not cross that line. All right, let's take a look at what a reflection over the x-axis would look like. Now this one on our first example, the parent function's a little bit different. It's -4 to the x. So I'm going to graph the original points here real quick, and then we'll look at the reflection. Okay, so this one, the parent function wasn't 2 to the x. It's going to be 4 to the x this time. So the points are slightly different, but it still looks similar to our original parent function. All right, so if I want to reflect this over the x-axis, what's going to happen is every point just gets flipped upside down. Okay, so we're just going to flip this whole graph upside down. So instead of the point 1, 4, 1, -4. All right, so let's try this one with our parent function, the second one. So we've got our parent function in here with the same one we've been using for the whole lesson. Now what would this look like if we reflect this over the x-axis because of that negative out front? So go ahead and pause your video and try this one out. All right, so each point is just going to get flipped upside down, and then just try to connect the dots there. We still have that asymptote at y equals 0, only it can't go above the asymptote this time instead of below. Okay, natural base exponential functions are exponential functions with base e. These functions are useful for describing continuous growth or decay. Exponential functions with base e have the same properties as other exponential functions. So what I want you to do is let's just go ahead and figure out what that number e is. It's kind of a number similar to pi that we can't write as a fraction. It's just it's not a repeating decimal, it's a non-terminating decimal. It's going to go on forever and ever. So why don't you pull up your calculator and figure out what e is. Okay, so on your calculator, you should be able to find a button that says either e or e to some power. So here it is on my calculator, e to the x. Now normally you can just hit the button and then say what power you want it to. My calculator, you actually have to do it backwards. So if I want just to know what e is, but the only button on my calculator is e to the x, I could just do e to the first. That will tell me what e is. So I actually have to type it in backwards. I have to do the power and then the button, but this is what it should look like in your calculator. So usually it's e to the whatever power you have. So e to the first power. What is e? It is this number 2.718, and then it's just going to keep on going forever. Okay? So 2.718. Let's write that out. So this I just got from your textbook. It says different ways of how you can calculate what e to the third power is. So you can do it just like we did and take e to the third power. We could have graphed it if you wanted to do that. And we could also use a table to figure out what e to the third. Notice e to the first right here is the number that we got for e. Okay, so what would e to the eighth be? So go ahead and calculate what e to the eighth would be. Pause your video and see if you have it correct. Okay, you should get 2,980.96 approximately. Okay. All right, so we talked about interest compounded annually in section 1. We're going to now compound interest continuously. So interest that's always building off of each other. And that's where that e comes into play. Okay, so the equation is the amount at time t equals p. So instead of our a, p is our starting value. Principal, it's called. R is rate and t is time. All right, so let's go ahead and try this first example. So we have $3,000, 5% annual interest accrued continuously, and we want to know what's in the account 4 years later. So go ahead and pause your video, set it up, and see if you can come up with the answer. Okay, so the amount after time t equals 3,000 times e to the, and then don't forget to change that percent to a decimal, 0.05 t, but now I want after 4 years, so we're going to plug in that 4, okay, and then go ahead and calculate that. All right, so if I want to calculate that, again, mine I have to kind of do backwards. I have to do the decimal or the exponent first. And do make sure you multiply those two numbers before you take e to that power. So 0.05 times 4, then I'm going to take e to that power. So notice I'm going to take e to the 0.2 power, and then times 3,000. Notice I didn't clear out my calculator. If I clear out my calculator and round it, we're not going to get the most precise answer. So don't clear your calculator out. So it should be $3,664. And since we're talking money, let's go ahead and round this to the nearest cent, 21 cents. So again, I want to show you what this will look like if I did round it. So if I said that's about 1.22, and then I tried it, 1.22 times 3,000, it's going to get off by $4. Okay, it's $4. So if that was your money, you wouldn't want to be shorted $4. So don't round it as you go. Just keep that big number in your calculator and then take that times your 3,000. So again, after 4 years, you should have in your account $3,664.21. All right, so your assignment, you've got a couple graphs to do, and then a couple of these continuously compounded interest problems.